Suppose there is a current carrying wire which is carrying a steady current in this direction, then it will have a corresponding magnetic field like this. And if there is a charged particle which is moving along this direction with a velocity v, charge q and mass m, then it will experience a magnetic force. But why it experiences the magnetic force is the question, which we will explain using relativity. So let's see how we can explain it, right? So to explain this concept, I'll be using very common example in relativity. So let's see. So suppose there is an infinite linear charge over here of negative charges, and just next to it we have infinite linear charge of positive charges, right? Okay. And it is going till infinity. This is also going till infinity. Okay. So suppose this negative charge is moving with a velocity v. Okay. And this is at rest. But we have to define the frame for relativity. So suppose there is a S frame which is at rest. Okay. So it is an inertial frame of reference. So with respect to this, it will first of all, let's define something. Suppose it has a linear charge density of lambda negative and lambda positive with respect to this frame of reference. Okay. So over here, linear charge density of negative of lambda, then lambda negative is lambda negative, and lambda positive is lambda positive. Correct. Now, with respect to this frame of reference, suppose if I choose a particle, suppose this is the infinite charge, and if I choose this portion out of that, suppose x is equal to a to x is equal to b, correct? So its length will be equal to b minus a, correct? Suppose this is L, right? Okay. So this is L, okay. So what is the charge density? Suppose in this region there is a charge q, correct? So lambda negative is equal to q by L, right? Of course, q will be negative in this case. Similarly, it will be q by L, right? You can write it as negative and this is positive, okay? Now suppose if I move to S dash frame, which is moving with a velocity v in this direction, suppose. So it is also an inertial frame of reference, okay? So with respect to this frame, if I see this infinite charge, this is at rest now. Relatively it is at rest. So it means if I again choose a portion out of this with same charge as we chose over here, suppose q, because we know that with velocity charge does not change. So now since it is at rest, so L dash will be equal to L naught divided by square root. What is L naught? L naught was L, right? 1 minus v square by c square, correct? Okay. So lambda negative will be equal to lambda negative dash. It will be equal to q divided by this length, L dash, right? Q by L dash, which is equal to q by L into 1 minus v square by c square, that is lambda negative root 1 minus v square by c square. And similarly lambda positive dash. Now again, with respect to this frame, this will start moving along negative x direction. Hence, with respect to this frame, it will have a lambda like this. Why? Because now it is moving along this direction, so its length will be contracted, which will be L by root 1 minus v square, it will be L into root 1 minus v square by c square with respect to this frame, right? So we have the relation between lambda dash and lambda positive dash, right? Now it's an infinite linear charge over here. We have infinite linear charge, so the electric field due to linear infinite charge is given as 2k lambda by r, right? So suppose there is a charge q over here, which is moving with the velocity v with respect to this frame. So with respect to this frame, this will be at rest, correct? Okay. So we can calculate the electric field Suppose this is at a distance r, and since they both are very close, they are at infinitesimal distance, so r will be same in both the cases. Hence, electric field is 2k lambda dash by r. Correct? Now, what is lambda dash? Lambda dash will be due to both of these charges, right? Hence, lambda dash is equal to lambda positive minus lambda negative. So it will be equal to lambda. So we have to first of all make it like this. So lambda positive divided by the quantity root 1 minus v square by c square minus the quantity lambda negative root 1 minus v square by c square. Correct? Okay. So now we can take lambda positive outside. So we will have this 1 minus v square by c square divided by the quantity root 1 minus v square by c square, right? Why I have taken lambda as common? Because they both have the same linear density. Okay, so basically it has also lambda and this is also lambda, right? It is just to represent the different charges. I have written it like lambda. Okay, so they both have the same charges over here in that portion. So we have electric field as 2k by r into lambda times the quantity v square by c square times 1 minus v square by c square. Correct? So this is the electric field over here, right? So what is the force experienced by this particle? It will be equal to QE 2k lambda by r into q v square by c square root 1 minus v square by c square. Correct? Okay. Now it will be along which direction? It will be along this direction, along j direction, along y axis, right? Okay. Now the question is, this force is with respect to S dash frame of reference. So what is the force with respect to S frame? So we all know an expression given as F. Now if you calculate along F along the x-axis, the force will be always 0, right? You can check it yourself. We know this relation from the inverse force transformation equations. We know that F is equal to Fy is equal to Fy dash, this of course Fy. Okay, root 1 minus v square by c square divided by the quantity 1 plus vu by c square, right? Now use the velocity of this particle with respect to this frame. So of course it will be 0. Hence we have just this expression that Fy is equal to this expression. Okay, so Fy will be equal to 2k lambda by r into q into v square by c square root 1 minus v square by c square times the quantity root 1 minus v square by c square. Now this and this gets cancelled. So we have the force is 2k lambda by r into q v square by c square. Now the question over here is that they both are almost at same distance. So the electric field due to this charge, this linear charge will be along this direction away, and due to this will be along this direction. So it means that they both should cancel, so the net force should be 0. But over here we have got some net charge. So this is the magnetic force, right? So this is the magnetic force, and that is why moving charges produce magnetic fields, right? So it is equal to 2k lambda by r q v square by c square. Now we can write lambda into v as the current. So we have 2k lambda, 2k into v, it will be I, qv by c square. So we have q, and then we will be having over here 2k by c square I times velocity, right? Now this expression is the magnetic field due to infinite line charge. And what is b? B is equal to ki by c square. So it is uh, 2I by 4 pi epsilon naught c square. Now epsilon naught c is equal to what? Well, we know the relation that c is equal to mu naught, sorry, it is equal to 1 upon square root mu naught square c, epsilon naught square, right? Hence we have c square into the quantity epsilon naught square, sorry, epsilon naught only, why I have written square, is equal to 1 upon mu naught, correct? So we have mu naught is equal to c 1 upon c square epsilon naught. So we have this expression over here. So this is simply equal to mu naught. So this is mu naught I by 2 pi. So from here we have the relation v is, f is equal to q v cross b. So that is why a moving charge experiences a magnetic force. It is due to relativity.